So here's the front page of the NASA Exoplanet archive. It contains hot links to several news articles, as well as basic statistics about more recent or more prominent missions, as well as some shortcuts to some of the tools that we will be using today. Before we get into the tools, the most useful thing that I know about how to use the NASA Exoplanet archive is to essentially look into a specific target. So today we are going to be first looking at, let's say, TOI 216. So you can go ahead and put in the name of the star or the name of the planet. The naming jargon is a little different. The normal TOI name usually belongs to the star itself, and then planets will have subsequent lowercase letters, usually B, C, D, E, and so on. These smaller lowercase letters are actually assigned in order that these planets were founded. So TOI 2016.01, or most likely 2116b is another naming for it, was the first planet. TOI 216.02, second planet. So this is a system of a little less than a solar type star. Right here you can see the stellar radius, or the radius in compared to our own star, as well as the temperature. And here we have the comparative radii of these two ones in context of Jupiter radii. So on this page, it is a small, relatively new system. And here you can see the method of which they were found, transits, the year that they were found, as well as their reference papers. These are very important to know and find, especially if you want background on a system that has been observed for a long time across multiple missions. So it links to NASA ADF's website, where you can find the publisher as well as ArcSiv sources for this system. So on every page, you will find the stellar parameters, where it gives you all of the information on the star that we are able to have with the technology that has been subjected on that system. So here we have some guy information, some publisher information, and it has a plethora of different values. And then below it, we have information on both the planets. TOI 216.02, you can have everything in terms of transit parameters, as well as periastron, orbital dynamics, approximate equilibrium temperature. This is great if you are specifically doing work where you are combing through one target at a time in order to... Okay, my bad.
You're doing great, carry on.
Sorry. So, especially if you are going through single targets at a time looking for anomalies like I have in previous research, it is great to know these specific parameters when you are looking for anomalies. You can also tell a lot by the possible formation of these systems from the parameters of the planets and the parameters of the star. So here we have TOI 216.02 and then 0.01. And then it links to the associated stellar parameters, which I believe will just take you, well, it should, if you don't have a trackpad, should take you all the way back up here and highlight where exactly these parameters are being linked from. The primary parameters that are being used for this specific page are coming from this publication. Whoops. So this is how you look at a singular system, especially if you are going into the background of it, or if you are looking for specific characteristics of that system, where you need to do a population study. These single pages are great for gathering that type of information, as well as seeing what other people have done to publish about it. To find all publishable materials on a specific target, simply hit bibliography. And here you can find all of the papers that either reference it or reference the system generally. This is especially good if you are writing a paper and you need sources to draw about this specific system or systems like it. So now that you've seen a single system, now it is time to consider, how do I draw information across multiple systems, a lot of systems? You might need to do a population study on systems that were observed in a certain mission. So under data, you will find all of these wonderful links leading you to a bunch of different source pages. And here we're going to go to the basic planetary systems. And this should take us to the confirmed planetary systems table. There we are. This is a very large table, and it consists of all known confirmed planets to date. And it tells you a lot about all of these different systems, when they were found, what the discovery facility was, what method was used to find them, how many planets are in that system. Go ahead all the way over to planetary parameters. To navigate specific statistics of this page, there are these little entry bars here that can help you narrow down some of your options. For example, if you're only interested in transiting planets, you can put in transit as the discovery method, and it will sift out all the ones that were found via transits. And there you go. All of these were found in transits. So what about if you want to find a transiting system or a planet that transits in the year 2009? There we go. And now you've narrowed it down even further. This specific portion, this planetary systems table, will be used in the tutorial later in this module. Oh yes, and then if you delete whatever is in these, it will reset into the full table. So that is how you use this. In order to download a table, you simply go into download table, where there are multiple ways for you to download it. One of the ways that I specifically have been taught to download is in tab separated or CSV format, and download checked and filtered rows, especially if you are doing a population study. And then from there, you can simply download the table, and it will download directly into your downloads folder of your computer. So that is all great and wonderful, I'm sure, but one of the best ways of using this data is to visualize it. One of the many tools that is used in this NASA Exoplanet archive, as mentioned before, was the Confirmed Planets Plotting tool. And here, you can really sort of play around and understand how certain populations of confirmed exoplanets are essentially influenced by our detection methods. So this is a basic mass and radius relationship graph, pre-generated, but there are all sorts of different ways of developing plots. You can do it by number of planets in system, perhaps. That's easy enough to do. All you have to do is choose your axes and redraw them, and they will label them out for you. So 1, 2, 3, 4, 5, and 6 separate numbers of planets and systems. Or you could do it by semi-major axis versus planet mass. And here we have an interesting collection of populations. Here you can see a very small but noticeable separation in these little clumps. This is usually done by observation bias from our instruments that we use, as well as where they are located. Not all planets transit. A transit is actually a very, very rare event that can only occur if we, as well as the system, has their planet pass in between us. So while almost 30,000 confirmed planets is certainly a lot, it is a mere fraction of what we could possibly be observing with the technology that we currently have. But what we have been able to discover, we've been able to find out many amazing things about the structure of planets, of planetary systems, and what's possible. Things like compact systems, where we can have 6 entire stable orbits within the orbital distance of Mercury of our own system. Those exist. Hot Jupiters, Jupiter-sized planets that orbit maybe 10 days or less around their star, stable orbits. And these graphs and this tool is a great way to visualize exactly what we have been able to find so far. So the last tool that I would like to outline with today is the Transit and Ephemeris Service. One of the main forms of research that I did as an undergrad before being accepted into research with Stephen Kane was a follow-up observation of TESS sectors. A sector is about a month long, and it is a portion of the sky. And TESS especially focuses on really bright nearby star hosts. So I would comb through all of these different light curves individually. And when I see something that looks like a transit, I would do one of 2 things. I would check to see if that system has a planet at all, as it should. And then secondly, if the Transit Ephemeris Service can give me a transit time window that lines up with the light curve. And this is essentially how this goes. So here you are at the Transit Ephemeris Service. You can do multiple targets. You can make a list of target names yourselves. You can also put in a single target, and we'll be doing that today using the same one. Let's say TOI 216.02. And then it will look around for sources that will get the ephemerides of the same one that you need. So here we have multiple sources, and to simply select one, you just double click or click on whichever one you're using, and it will autofill all the transit information that it needs to get your transit windows. Over here, you can do observer location. You can do space observatory or an Earth observatory. Let's say for this example, we can do Mauna Kea. And then finally in the observing window, the next event is especially helpful if you are in observing, but what I usually use is this, the window of the past dates, AKA I would put in the dates for that sector of time that this object would be observed in. So if we were to do, well, for this case, let's just do next event, and then go ahead and hit predict events. And as you can see, there are no events, because if I am correct, this one probably cannot be observed by Mauna Kea. So if we do independent of observer location instead, there is one event found. And it gives you essentially when the next transit would occur. In this case, it will be July 5th at 7:55 in the, well, that's the event midpoint, in July 5th. Sometimes they also include a start and end calendar if you choose a specific observatory to observe from. But this is a really great tool if you are double checking, looking for anomalies in pre-existing data. Multiple new planets have been found via this method. And that is exactly what I was aiming to do through that research. If you recall, there was a news story, I believe 2 years ago, about a 17-year-old NASA intern who did exactly this, and he found a new planet. Although the details of that story are up for debate. So that is a very general overview of the NASA Exoplanet Archive and what you're able to do with it. The amount of tools and the amount of data available in this site are, quite frankly, way too extensive to be covered in today. So to end this, I'm going to go over the tutorial that was created by our own Joey Murphy here, to help you kind of visualize how exactly to take data and how to use it in Python. So in this notebook, which is available on GitHub, I believe, or otherwise, It is essentially going to tell you how to do a mass-radius relationship from the Exoplanet archive for Kepler and how to visualize it. And then on your own, your job will be to create a period versus radius relationship, as well as to plot any two parameters you want. Be sure to label your axes with units. So in this first one, very basic, we import our OS, pandas for data management, NumPy for math, matplotlib in order to graph, as well as matplotlib inline to essentially put our graphs to the side. This, in short, makes it run very nice. It makes it look very nice. So I'm going ahead and run that, make sure that that is all taken care of. And then for here, it is going to take in data. This file should be available to you previously in the data file in week 3. So it's going to load that in. It is essentially looking for a folder named data and then a CSV file called confirmed example. That name and that formatting is very important. Do not change the names of these files. So it's going to read in the CSV, and this is essentially what it pulls up. It gives us all of this information about these targets, the way that they were discovered, their orbital periods, a lot about their orbital periods, their masses, and the like. So what are the dimensions of the data frame? This essentially tells you how many rows and columns there are. Pandas likes to keep things fast and clean. So while we asked pandas previously to show the maximum amount of columns right in here, it does not show all of the rows to make sure that it puts out what it thinks you need to see. So now we're going to make a quick mass radius diagram. Here for matplotlib, we will essentially plot from the file these two columns, the mass and the radius in Jupiter mass and radius, as well as some basic visual parameters. This dot here is meant to make small unconnected dots rather than lines. The alpha is meant for transparency, so that we can see more of the dots, as well as a density check. Go ahead and run that. As you can see, it comes here. However, it is scooted off to the side. This is a problem usually when a lot of certain points are propagated into a small amount of space. To fix this, a very common way to do it is to simply introduce logarithmic axes. And this way they become more spread out, and the relationship between these two parameters becomes a lot easier to comprehend. So here we can see that there's 762 different planets represented here. The mass is in Jupiter masses and the radius is in Jupiter radii. And there are two kind of main populations here. A large one is up in the center, no, upper right. It's very dense and it's very propagated. And this is actually at around 1 Jupiter mass or so. It is much, much harder, or at least there are less planets that we find here that are less than 1 Jupiter mass, but they are there. So here it will tell you how to download a sample of exoplanet, how to download the next file. You go into the Exoplanet archive, you go to confirmed planets, you will add the columns of mass and radius in units of Earth mass and Earth radius. And in order to get specifically Kepler planets, you can put in discovered by Kepler via the transit method. So we can go ahead and I can show you how to set that up. Go on over to data, planetary systems. Let it log in. Okay. So as I mentioned before, you will want the transit method. And then when you get to Discovery Facility, if you click this little question mark tab, it will show you a lot of really useful commands that you can put in here. So if you want a string match, you simply just have to type in Kepler. And if you want to exclude targets from Kepler, i.e., if you are looking for transiting planets, but maybe with the TESS satellite or others like it, Kepler is responsible for a lot of transiting planets. So if you don't want Kepler planets, you can simply put not like and then what you want to exclude. So here is the resulting large set. And in order to select which ones you want, you simply put select columns and then you select your columns from the drop-down menu here. To make it easier, you can simply hit quit clear all, and then you are able to select without having to unselect what is already here. So after you download all of that with this, with these directions, and then save it into your data file to make sure that your computer can find it again, that OS can find it, go ahead and load it in. It will give you a size. That's how you know that it works. Load in the new data set. And this is what you should end up with. So then we're going to make a histogram to see the number of planets versus Earth radius.
Go ahead and wrap up in the next minute or so, Emily. We can leave the rest for exercise for the student if you don't get to everything.
So, long story short, NASA Exoplanet Archive is a great portal for getting large amounts of information about confirmed systems. You could do anything from manipulate the data that is already in there once you have downloaded it, or specifically filter out what you need for smaller population studies. Your homework is also within this same Jupyter notebook, so please look for it there. And thank you so much for listening.